push here. I would share the whole screen because I'm going to because otherwise when I put my full screen, they're going to yes. Okay.
And he was thinking.
Oh, because it is a website. It's not a PDF.
Okay, but is it okay?
Yeah, no, it works fine, but you should share like the whole screen, not just the application.
Okay, so you need.
No, in the share.
Share.
Yeah, and say screen. Yeah,
This screen.
Yeah, because otherwise you're just sharing one application.
Okay.
And probably when I go full screen.
Yeah. You use as a software.
Yeah, it's just a website. It's slightly magical. This is just simply a website for my.
Okay.
And it has its own buttons, which are website buttons. And this is because it's the only way I found to play videos inside of the presentation.
I see.
Other than PowerPoint.
Okay. I see.
Yeah. No, it's fine. I don't think there's anything that far to the side. Okay, let me say okay. Yeah, at the moment. No, I was checking that is what the slides.
Yeah.
I knew that they had a great Okay, so let's resume the afternoon session. So it's my great pleasure to introduce Professor David Gomez Castro. And the title he will talk about the boundary singularity for fractional, elliptic, and parabolic problems.
Yeah, thank you. So let me start by thanking the organizer, in this case, especially because they have been doing a huge work in organizing this series of conferences, not only this one, but I've been here for at least a month. I know these chairs better than my home now. People of immense level have passed through here. You can easily see in the schedule that we will have Figali in a few days. And so in this case, a very special welcome. So I will start talking about the fractional placing in RD, and I want to convince you that there's, at least by saying that very famous people have worked on this, that probably it's interesting. Then I will talk about fractional applications in bounded domains, which is what I want to talk about. I highlight the S. There's multiple fractional applications, and I want to talk a little bit about the different interpretations that one can get, a little bit about the functional setup, and then I will talk about large solutions. There is solutions that are not bounded, and there will be some surprising solutions that are not present in the S=1 case, in the usual application. And I will see how they appear by reviewing the usual applications. So some of the computations, the only difficult computation is very naive and should be taught in the master courses, probably is. And then I will talk about the singular problem and extensions. So let me talk about my co-authors. Juan Luis, I don't know if you know him, he's here. And there's Nicola Batangelo from Bologna and Hardik Chang, who is now in Basel.
Oh.
What?
I was saying hello, Chang.
You know, it's not live. It might be connected, but who knows. So first, let me start talking about the fractional placement in RD. This is the guy, maybe some of you know it. It's a local operator that looks kind of like the Laplacian. It uses a principal value, and a principal value is just remove a small ball, compute this thing which then works, and then let the ball go to zero. This is a reasonable thing because of cancellations. There's 10 equivalent definitions, so you can pick your favorite. One of them is that it is the operator that has Fourier symbol psi to the 2s. So in this sense, it's a fractional appellation. It's also the infinitesimal generation of a Levi process. So instead of linear motion, you get a process that does long jumps, and you can read about this. I will not make a lot of comments on this. If you work in RD, you can look at the Laplace equation. And in Fourier, you just transform, you get the side to the 2s. So it's very easy to solve. The inverse Laplacian of solving the Fourier multiplier is just the Riesz kernel, so you have a nice solution. It's an integral, so it's explicit. What more can you ask for than an explicit representation of the solution? And there's a constant that you need for this to go as s equals to 1 and s equals to 0 to the identity. And in fact, you can do this also by looking at the minimization of a free energy functional, which is related to the Gagliardo semi-norm and to the fractional homogeneous Sobolev spaces. I will say that there's a nice paper on that by me, Juan Luis, and Lorenzo Brasco, which came out last year. So people have done all sorts of stuff. First, there's been a nice analysis of the operator. Caffarelli and Silvestri proved that you can come to this operator by an extension. This paper is hugely famous. You can look it up. It has thousands of citations. People have done the obstacle problem. So just to cite some people, Silvestri again, this was part of his thesis, and then Begoña Barrios, Alessio Figali, and Xavi Rosoton, just to cite some of the Spaniards and Alessio. You can do the heat equation, but because you solve in Fourier, and this is easy. There's a porous medium interpretation for this, and now I shamelessly make publicity for the people in Madrid as well. Toro de Pablo, Fernando Quiroz, Ana Rodriguez, and Juan Luis again, and then another paper by Juan Luis and Bolzone, who you will hear here in a few days. There's connections to geometry. Mar Gonzalez has a nice paper on this. And people have looked at the semi-elliptic linear problem. I will cite more papers in bounded domains later, but you can ask Professor Veron, who also knows a lot about this, and Professor Nguyen, which is back there. And there's also a nice paper again by Mar and Bruno Bolzoni and other people. This porous medium thing that I mentioned is not this other porous medium type, which is some people call it the porous medium with fractional pressure. You will hear a talk about this by Espen Jacobsen in a few days, 1 or 2. For m equals 1, this is known as the Caffarelli-Vázquez problem, and if m is not equal 1, then you can then there's a lot of theory by the group in Madrid, so Juan Luis, and you can ask Diana, you can ask Felix about these things. There's numerics. I will do some videos. So one of the first papers that I know about numerics is a paper by Espen and Carlsen about discontinuous Galerkin, which is, as usual, finite elements are difficult to write. There's finite different schemes like this one, and there's a nice paper by Felix, and also you can ask Felix and Espen about these finite different schemes. So this is the fractional Laplacian in the whole space. When I came to this game, it was 2018. You see, most of the references are older, so people knew a lot about this, and I learned from Juan Luis most of the literature. But people were becoming more interested in the case of bounded domains. And then I say fractional Laplacians, because I told you there's 10 equivalent definitions of the Laplacian in the whole space. But then if you try to interpret the things in bounded domains, you get different things. So you can take the formula for the whole space and then use it in a bounded domain. You're free to do it. You take omega, but when you compute the fractional Laplacian at one point, you look at the whole universe. Then you will need to put boundary conditions outside everywhere. You can look at the Laplacian in a bounded domain with Dirichlet boundary conditions and just do the spectral power of it. So define the operator that takes the same eigenfunctions and the eigenvalues to the power s. This is another option. It's not equivalent. And then you can take the sensor fractional Laplacian, which is this idea that you use the same integral, but when you're in this point and you want to integrate, you integrate only in omega, and you don't look outside of omega. And these three guys have different interpretations from the point of view of, they all are related to this Levi process with long jumps, but the long jump might escape omega. And when it escapes, you need to do something. You can choose what to do, and every choice will give you one of these. Matteo knows this theory very well, you can ask him. So both the restricted and the sensor fractional ablation are related to free energy, to energies in this form, whereas the spectral fractional ablation is just a power. So it works nicely. You can do the theory for all of these guys easily. They have positive phase eigenvalue, a nice theory of energy solutions. And if you want higher regularity, then you have to ask other people. So there's a very famous paper by Xavi Ross and Joaquim Serra about the restricted, and the sensor was done in several papers later. The good thing about all of these guys, the three guys that I mentioned, is that they have more or less similar green kernel structure. So these are all linear problems. They admit a solution which has a green kernel, and the green kernels look more or less the same. And so you get the behavior of the green kernel in the whole space. This gives you the tails, and then you have to correct it on the boundary. And the corrections to the boundary look like the minimum between 1 and the distance to the boundary corrected to a power. The S is the S that comes from the Laplacian, so it will be the S fractional Laplacians, and the gamma depends on the precise choice. So, and people have done this computation, usually through probabilistic methods. And so you get gamma equals S in this paper, gamma equals 1 in this paper, and gamma 2S minus 1 in this last paper. And the CFL only makes sense if S is greater than 1/2, otherwise it breaks down. And so it kind of looks like this. You have S and gamma. The spectral is always gamma equals 1, which is also the behavior for the, here at S equal 1, gamma equal 1, you have the classical Laplacian. The restricted start at 0, and the CFL start at 1/2, and it's a linear going to 1. Okay, so for the numerics, these three cases have numerics that you can do. For the restricted fractional Laplacian and the sensor fractional Laplacian, you can recycle the methods for the whole space with a little bit of work. I don't want to go into the details. And for the spectral, you can just do a numerical method for the Dirichlet problem. So for the usual Laplacian, this matrix in 1D does the trick, and then do the spectral power of this. Because this matrix has roughly the eigenvalues of the continuous operator and the eigenvectors in discrete form of the continuous problem. So doing the spectral power of this, which is diagonalize your matrix, take the diagonal, put it to the correct power, that is a good choice of a numerical method. There are better methods. Felix knows them all. You can ask him. And you can also do finite element methods, which are a little bit more difficult because you have to deal with these integrals. And but there's a nice paper about the spectral, also by Felix and the group he was working with in the camp. So for the functional setup, let me just think about which functions I'm allowed to give the green kernel. And if you give the green kernel a function, and you look at what happens in a compact domain, you will get that it's integrable in this compact set away from the boundary by a constant and the integral of f multiplied by the distance to the boundary to the power that is in the kernel. And so S for the restricted, 2S for the sensor, and 2S for the spectral, and 2S minus 1 for the, no, S minus 1 for 1 for the spectral, and 2S minus 1 for the sensor. So this takes things which are in this integrable space and gives you L1 log functions, which for the green kernel is good enough. Let's see later what happens in the boundary. And in fact, you can do the Hoff estimate and take an f which is greater or equal than 0, multiply, integrate, and realize that also this is missing a gamma, but your solution is bounded from below by delta to the gamma, and then the integral of s times delta to the gamma, this in x and this in y, meaning that if this quantity is not finite, this number will be constantly infinite. So if you are not in L1 omega with this weight, then you plug the thing into the green kernel, gives you plus infinity at every point. So precisely the good place to work is L1 omega delta gamma. This is the reasonable data to fit the green kernel. Okay, so in order to define solutions, a very smart idea, it's not mine, I will tell you later who it is you multiply by a test function. This, you know, is not my idea. You integrate by parts, also not my idea, if you can, but say you could. The problem is that each of these operators have domain of the operator which is different, and this makes life difficult if you want to study the three of them at the same time. So what we do is we replace L of phi by some psi, which is compactly supported, and move the L as an inverse to the right-hand side. This was an idea that originally occurred to Matteo, Yannick Sire, and Juan Luis in 2015. And so this is a nice formulation where by involving the green kernel, you can take test functions in an infinity with compact support, and your life is easy and uniform through the whole range, but you've involved your green kernel in the computation. This allows you to do wonderful estimates I will not talk about. Okay, now I want to talk a little bit about large solutions. What is a large solution? An unbounded solution. Bounded. I will mostly care about things that blow up on the boundary, but you've seen here things that blow up everywhere. And usually maybe a semi-linear thing like this. Okay, for the usual Laplacian, we know that the Keller-Osserman condition works for things that look like this. I like to put my sign in the right order so that people don't get confused. This is the Laplacian, our Laplacian. And this has also been done in the fractional case, and you find solutions that blow up on the boundary. There's a whole list of works. In particular, Veron and Nguyen have this really nice paper for the restricted fractional application. But so we wanted to understand if you could do this without Keller-Osserman and if there was something extra there, right? So we did the following computation with Nicola. We said, okay, plug a power of the distance to the boundary into the green function and see what comes out. And then you roll up your sleeves. This is horrible. This green kernel thing has many terms, so you have to integrate. But the result looks like this. So you can plug things that are, this corresponds to the limit of the L1 omega delta gamma, the domain of the green kernel, and then you move upwards. So as you improve, something delta to some power with power that improves, precisely when you reach minus 2s, what comes out is bounded. So in all of this range of beta, you get unbounded things here. Then you go all the way up to the behavior of the eigenfunctions, which is this one. And then from there, you're constant. And then in the middle, there's a log behavior. If you really must see the formula, it looks like this. Delta gamma in this range, delta gamma with a log correction here, delta to the beta plus 2s, and plus infinity if you're not in the admissible range of the function. So you plug a power of the distance to the boundary, one of those come out, and you see when you have bounded solutions. So in fact, you have unbounded solutions in many cases. For beta in between minus 1 minus gamma and minus 2s, you get something that's not infinite, it's not constantly infinity, but blows up on the boundary. And in fact, if you look at the minus Laplacian, gamma equals 1 equals s, there's nothing here. The range is empty. The Laplacian, you cannot feed it the distance of the boundary and get something that is unbounded. In the Laplacian, this does not happen. But it happens it happens in the restricted fractional Laplacian when you get minus 1 minus s. So I made a video with the numerics having something slightly better. And this is what it looks like as you truncate it and make the truncation go up. You will believe me if I tell you that that's going somewhere. That is infinite on the boundary but finite. For the spectral, the value is minus 2. The blow-up range is the blow-up exponent is minus 2 that you feed into the Laplacian. You get something that is finite. And the same sort works like the usual Laplacian. And you get something that converges to, and in fact, I will show you in this problem, you can actually do Dirichlet boundary condition. This was known by a work by Chen. More surprises. There's a surprising solution by Bogdan that says you can put 1 minus x squared to the s minus 1. So this is minus 1 minus s. This blows up on a ball on the boundary, is 0 outside, and it is harmonic on the inside. So there's something that is not zero, that blows up on the boundary, then continues as zero, and is harmonic on the inside. So apparently, giving the value inside and the value outside, or away from omega, is not enough to have uniqueness of solutions if you do not ask for your solution to be bounded. You have to, if this solution is unbounded, in the range of bounded solutions, you are limited by giving F, and if you want the outside condition, call it G. But otherwise, I will show you that I can give you an extra condition, which is the singularity at the boundary. So there is an extra condition. Okay, let me talk before I spill the beans about this case, about the usual ablation. Those people that disconnected about the fractional stuff can come back. I'm going to compare that problem to this problem. Innocent enough. So what do very weak solutions look like? Well, if I take something which is, this should be a 2, I take a nice test function and I integrate by parts. In this problem, I get this. In this problem, I get that. Obvious. Now, my question is, are that problem and that problem related in some way? I mean, in the very weak formulation, they kind of look similar, right? If I could make this look like that, that would be nice. Could I make some sequence of data for this problem that leads me to this problem? Well, the answer is yes. I remind you that you can take the boundary of the domain and do a tubular neighborhood. And the tubular neighborhood is just you get to one point of the boundary, you look at the normal, outside normal, and you go backwards with a number R. And this maps, it's a bijection, even a diffeomorphism of a neighborhood of the boundary into this set. And if I take something that is in one of the boundary, I can extend it into this tubular neighborhood by just doing the tubular thing, and this is fine. It's a little bit of work, but you have the Jacobian that does the right thing. Okay, so what I'm going to use for that is I'm going to take my boundary function, extend it a little bit to the inside, and then do the characteristic function of a small side, divide by delta, which for the Laplacian, by the distance to the boundary, which for the Laplacian is the critical value. Remember that Fm times delta in L1 was the requirement for me to have something in the green kernel. And then I normalize to get something nice. And you do it, you integrate in a neighborhood of the domain, and you get precisely the result. So by locating the interior data very close to the boundary, as you move it, you end up with the Dirichlet boundary problem. And in fact, I have some numerics. You do this in 1D, I'm doing S equal 1, and as I locate my data closer to the boundary, you see how I approach the constant solution 1, which is precisely what we wanted. This works in higher D, and of course, if I can put a value here and a value there, and you need to modify this slightly, but it works, and it works in any dimension. This is fine. For the classical ablation, by locating F close to the boundary, I can create, or I can approximate, the Dirichlet boundary condition. So what happens when, and if you do look at the green kernel, what you are getting is the minus normal derivative of the green kernel, which is the Poisson kernel that we all know and love. It's the kernel that comes from the Dirichlet, non-homogeneous Dirichlet boundary value problem, which is great. So what is the Martin problem? I will do the same. I will localize my delta to the boundary, and I will show you that the green function of this goes to something which is not 0. And in fact, it will be something that has operator 0 on the inside. On the outside, if it's defined, is 0, but I can divide by my function, and this has a limit towards the boundary, and this gives me an extra condition. I will be able to give here any data in L1 of the boundary, and this problem will have a non-trivial solution. Of course, if you ask for the problem, the solution U to be bounded, this condition can only be H equals 0, and then you have uniqueness. So uniqueness in the usual case, we didn't break the uniqueness in the usual case. The range, the rate of this guy is like the distance to the boundary to the power 2f minus gamma minus 1, which for the restricted fractional Laplacian is s minus 1, this rate was known. For the spectral is 2s minus 1, this rate was known. And for the sensor is 0, which means it's bounded, which means I can actually give Dirichlet boundary data in a proper sense, U has value H on the boundary. And these two ranges were known. In fact, Nicola knew them from previous papers that I will mention, but they didn't, nobody knew how they were related. And they are related precisely by this gamma that allows us to interpolate between the restricted and the spectral. 2s minus gamma minus 1 is the range. So for the restricted fractional ablation, this was known by work by Avatangelo during his thesis, and for the spectral, it was known by work by Avatangelo in his thesis. Chen proved this in 2018 for the CFL, and then we did the whole theory in 2022 that covers unifying the theory in this way. So let me show you how I localize this correct data to the boundary. It has the correct scaling. And in fact, you see that we get the singular solution for the spectral, for the restricted first, for the spectral second, and for the sensor, we get something that approximates the Dirichlet boundary problem. If I wanted to have value 1, then I would normalize with the correct value so that it would go to something. All of these pictures we made because Juan Luis said he wanted to see the ears of the cat. I needed to do something. Yes.
So what is S? S is the same in all of these pictures, 0.9? The order of
yeah, I think in this last one I changed the number, but the number is the one that I was using. So 0.75, that's roughly the same. I don't, so it's always the S is always the exponent here, but for some reason I forgot to run the last case in 0.75.
And there is a blow up on the boundary, even if S is very close to 1.
Yes.
In the other cases.
Yes, but so the Bogdan solution is precisely 1 minus x squared, minus 1 minus s. So it blows up in all the cases. Except when you reach 0. But the blow up is, of course, becoming less and less. If you want to do the limit, of course, you must put the condition so that you get something, and then this converges to 0, even though it's breaking up in L1 log.
The calculations match the theoretical computation.
Yeah. And then in the spectral, you normalize with the 1, which is always 1, and in the sensor with the 2s minus 1, which is you normalize precisely with the thing that when you plug it into the green function is terminal. So this is the terminal one, and before I showed you the pre-terminal one, which has the same behavior, but you cannot set singular boundary data. And so you do, if the idea is that if you do the same thing with the function that I showed, you precisely divide the green kernel by this boundary behavior, and you end up with something which is called the Martin kernel. You have to assume that this quotient has a limit because I had only assumed upper and lower bounds. So in order to get this, you have to assume this, which is true in all of the 3 examples. In the paper, we give the references where people have proved this. And this, you can call this gamma normal derivative of x on the bound. And the Martin kernel, by just simply doing the quotient with the distance to the y, distance to I to y to the power of gamma, as you go to the boundary, the estimates for g gives you this estimate. And naturally, U star is just what happens when you set h equals 1, and then when you integrate this against 1, you get the rate that I promised earlier. And in this case, there is no log correction in the singular case. This was interesting to us. And so there's a theorem, not only pretty pictures, but a theorem. So if you take something that is in L1 of the boundary, you go to something, the something satisfies this weak dual formulation, where you have h and the gamma normal derivative with the right sign. This was the usual formulation that people used. If you put it back in terms of phi, so L of phi here, this would be the correct normal derivative of phi, which was the formulation used for the CFL, and for the other one, you get something very simple. So you can do this in the specific cases by integrating by parts. So if U in L1 log is such that it satisfies D, then U is precisely integration against the Martin kernel. And if your H is continuous on the boundary, then you reach the boundary continuously. Point one. So it's nice. What about L of U? Well, the thing is that since I'm working with the green kernel, I never really defined L in the general cases. But formally, you will allow that if there is an L, which in the 3 examples there is, L of UM is 0, except for a neighborhood of the boundary. So L of U, L of the limit, is 0 in any compact subset of omega. And so formally, L of U equals 0. But our notion of solution is this. So any solution is the correct one, the integration against the kernel. And this is just Fubini's integration by parts. Some extension that we've done, we've looked at the problem, at the Schrodinger type problems with a lambda and what happens as lambda goes to eigenvalue. And as lambda approaches the spectrum, you get the expected stuff. We did another paper with Hardy where we look at the parabolic case. And the parabolic case, then you have to construct the heat kernel, and the heat kernel can be constructed very much in the same way as we construct or we can prove that this works as well. And I didn't put the limit, but the idea is that the quotient with the singular behavior can be set. And you can set an F, and you can set an H, and you can set a new 0. And if you're in the restricted, you can also set the value outside. But if you're in the spectral, you do the spectral with 0 boundary conditions. And if you do the censored, this is the condition for the sensor. So you don't have anything outside. And the idea is the same. You do the theory with H equals 0, which for most cases was done, but you generalize it, so you check it in the general setting. Then you localize H to the F to the boundary, and it works. And we've even done it for the Caputo and the Riemann-Liouville time derivative with the suitable initial conditions, which for people that know Caputo and Riemann-Liouville, Caputo has nice initial conditions, but Riemann-Liouville has a very weird initial condition. But this works as well. And we construct not the heat kernel, but, well, in some sense the heat kernel, but these guys do not generalize in my group because they have memory. So you have to integrate in a weighted way. But it works. And this paper is in the archive. Since it does not have a year, let me singular solution for space-time fractional equations in a bounded domain. So thank you for your attention. I'm happy to take questions now, coffee, or if someone wants to send me an email and be almost completely anonymous, I'm also happy to answer by email.
Question and comments?
Question, can you go back to your last equation, the fraction? Okay.
This one.
So big domain omega, big range omega of alpha between 0 and 2. How about
Alpha is usually between 0 and 1, so you do fractional less than the heat equation, which is 1. But probably it could be done for alpha greater than 1. It's basically
it's no more parabolic.
no. Then is
It's between 1 and 2 is a bit hyperbolic.
it's a bit hyperbolic, but it's the room telephone. Someone is calling us all. So you can do. So the idea for this is basically to construct the thing is that your operator has a spectral decomposition. So you do the spectral decomposition, and now you solve the ODEs. You can solve the ODEs for alpha greater than 1, I guess, but I don't know what the solution is.
I guess you only do alpha between 0 and 2.
So alpha here is between 0 and 1.
So when alpha greater than or equal to 2, we become to the wave equation.
Yeah, I would guess it would become some kind of wave kind of equation. But again, the idea is that you do the spectral thing and you look at the spectral. So basically, you just have to solve the ODE, right? You have to understand what is the behavior of your favorite fractional time derivative of x plus lambda I times x equals 0 when x is 0 to infinity with r. And these are the eigenvalues. And the nice way to do this is this fractional thing. What it has is a nice representation in Laplace transform. So you Laplace transform and you solve there. Then when you come back, you end up for alpha in between 0 and 1, you end up with a mid-Alexander function. For alpha in between 1 and 2, I don't know.
I think you still have exponential gain in lambda. But when alpha greater than 2, you will have the first. You have the exponential of the complex multiply lambda, something like this. Then
Okay.
that will be the dispersive equation.
Okay, we can look into that if you want.
And yes, can you go back one more slide?
Yeah.
So, okay, so what is your result really here? I mean, what is it that you prove for this problem?
Oh, that this has a solution in the weak dual formulation, and that the solution is given by integration against the correct kernels, so that it has the right structure.
And
Roughly the Duhamel formula for this.
And the H and the U star, H was, so which,
Oh, U star is the same as in the elliptic problem. It's just this function that you construct from the ring kernel. H is something that can depend, H and F can depend on time.
But U star is singular, so the boundary data are singular. You cannot put regular boundary data. That's the point.
The idea is that U x d basically delta x to the 2s minus gamma minus 1. You can set this as h t comma x, and this will be satisfied in a. This will be satisfied in a reasonable way. So if your data is only L1, it would be
and
in
the
average set.
regularity of H is bounded, L1?
H,
You can put L1.
you can put L1. It has, I forgot if it needed some regularity in time, but I seem to recall this can be, well, yeah, T for all. But you can probably do measures as well.
Yeah. If the different behavior of Levy processes near the boundary, they have a tendency not to see the boundary. So you have to put enormous amounts of boundary data for them to see it. And what you put is in F inside, and move it to the boundary, they try not to see, but if F is large enough, you get a limit.
Yeah, so the,
Large solutions, in the sense that they don't have to use it, will be lookable by the fractional operation. Otherwise, it doesn't see that.
yeah, the idea is roughly that you
have
can put here whatever H you want. H of T.
there is also a zero boundary condition here, right?
But no, but the point is that if you're doing the restricted, you can put the like.
Yeah, but
So-
also in the, I mean, also in the spectral, there is a zero boundary condition.
Yeah, but it does not care much.
The
My-
idea
my
that
point is
the
that-
boundary condition is exterior condition normally.
No, but for the
No.
spectral is like the right one. But the point of this calculation is that imagine that we're in the spectral. If we're in the spectral, we get gamma equals 1 at this whatever. My point is that I take your spectral problem, I feed it something which is here, and then I've gotten something that is singular on the boundary. So it has forgotten about your Dirichlet boundary condition. It sees the Dirichlet boundary condition here. So somehow the way I think about this is that you've done the spectral fraction of the operator with the boundary condition. So to some extent, you've lost a little bit of that guy, in some sense. So
Could you say that you said there is non-uniqueness, right? Unless you assume bounded. So you are sort of
well, I mean, there's uniqueness. I give you this guy, so here, and this gives you I could. My point is that
sorry, let me restate.
Yeah.
There is non-uniqueness unless you specify your boundary condition.
But the boundary conditions that you can specify are really very
Yeah.
determined, clear. As
Yeah.
the H times you tell, you cannot eliminate, you cannot put any kind of smaller boundary conditions. It's like a spectral graph. In the middle, there is no boundary conditions. If they are less than H times U star, the operator will not see them. You cannot solve this problem.
So if they're a little, if you ask that they're a little less singular than the really singular one, then you get uniqueness. So in this range, you can get uniqueness by simply saying they're bounded. Here you have to say just that they're a little less singular than the boundary condition.
It is not only that there is uniqueness, there is non-existence. You cannot get these boundary conditions. Stop.
Yeah. So the thing is that if you are looking, so if you are here, you cannot have bounded solution because you feed it to the green kernel and it's never gonna happen. So then you need something. If you allow for, well, the idea is that you can always build U as the green of F, and then add the M of H for any H in L1. This behaves like delta to the 2L minus gamma minus 1. And this is less singular than that. So if you want to be very general, you have to allow these guys. And if you don't want to see the singular boundary behavior, you have to give me an extra condition that says that H has to be 0. So this is near the boundary, this is much less singular than this other guy.
So my understanding then, correct me if I'm wrong, is that you sort of impose 0 boundary condition, but if you allow blow up, if you don't assume the solutions are bounded, you have non-uniqueness unless you have your extra condition on the boundary.
Yes, so somehow the thing is that
The
thing is that you didn't.
What happens also in the standard boundary problem? You can impose right-hand side plus boundary conditions. The only point is here, the only acceptable boundary conditions have a factor that is U star.
But I'm sorry, but you have imposed boundary condition twice. Because you're using the green kernel with the 0 boundary condition.
Okay,
but it's a different linear.
but let's do a thought experiment, right?
So this is linear.
This you've done the spectral fractional operation of the Dirichlet, the spectral power of the Dirichlet fractional operation. But now that H equals 0, this is the identity for odds.
We have two choices: putting F and H equals 0, or putting F equals 0 and putting H. It's okay, it's linear. But there is no other choice of boundary conditions.
But the
rest of
point,
boundary conditions will not be seen.
when you set S equals 0, you just have the identity. It completely forgot the Dirichlet condition.
Okay.
And then it sort of loses the condition for a while. And as S goes to 0, you lose it almost everywhere. Of course, at S equals 0, you just have that this goes here, and this is just the identity. So basically, if you say that for S equals 0, you will be as singular as F. And then in the middle, it's kind of forgets. And I think this is somehow related to the 0 boundary condition for the fractional overlap spaces. If you try to do H S0 for S less than 1/2, it does not care. It's allowed to jump on the boundary. Doesn't see the. This is in the sense that you're doing C infinity with compact support. So the point is that we saw the green kernel and we wanted to understand what it meant when you gave it singular stuff. And when you give it really singular stuff, that's really weird.
But this is something that people in probability knew. The only way you can see the border with a degenerate process is having a lot of information on the boundary. It has to be degenerate, singular. Yeah. So this is what the famous function by this Bogdan guy.
Yeah. This. Okay.
Yeah, so this function is good for us. In the sense that.
I think there is another question, but
I get probably you need the C1 boundary, C1 domain, C1 domain, right?
yeah, we did that proof in supposing that we have a smooth domain,
So
which is when your green function and your eigenfunctions have this uniform
Tubular neighborhood.
yeah, this uniform tubular neighborhood and also this uniform distance to the boundary. Because if you consider a square, which is the nicest thing for me that is not C1, then the eigenfunctions are sine times cosine. So around this point, the first eigenfunction is like distance to the boundary square for the usual operation. So it's worse. So the green kernel cannot have this wonderful estimate, and then our life is horrible.
So okay, can we have the Wiener's theorem for the functional operator?
Wiener result,
The more
Wiener test, I think.
Wiener test, I have no idea.
Yeah.
Juan Luis says yes.
So,
So maybe now, the center speaker. Tomorrow, the session will start at 10 a.m.
Thank you very much. And so do you know the fraction of function?
There might be, yeah. So you can take the usual operation with normal boundary conditions and do the power, so the spectral power.
In this case, okay.
Yeah.
More like
I want to
Neumann boundary version.
Yeah, for the restricted one, there is Neumann